Hey guys, this is Miss Pascual, or you know me as Sensei. I am going to be doing the test review on rational functions and variation for your test this Tuesday, March 4th. Are you going to help me?
I'm busy.
Fine. So our whole unit on rational functions is dealing with the transformation of the rational parent function, which we knew to be f of x is equal to 1 over x. Rational means it's a ratio, it's a fraction. So our parent function looks something like this, where we have a horizontal asymptote at y equals 0 and a vertical asymptote at x is equal to 0. Horizontal asymptote is y equals 0 and our vertical asymptote is x equals 0. Now a little bit about asymptotes. Asymptotes, we see them as dotted lines, but they're not actually part of our function. They're just used as guiding points. So the properties of asymptotes, whether horizontal or vertical, is that our graph is slowly approaching it, but it will never ever reach it. It will never ever go past it. Same thing with a vertical asymptote. It'll get closer and closer and closer to it, but it will never ever reach it. It's a very sad, tragic love story. So on this review, we have places where we have to identify the vertical and horizontal asymptotes. But you need to remember an important property of each of these. That when you have an equation of a vertical line, it's going to be x is equal to some number. And if you have an equation of a horizontal line, it'll be y is equal to some number. So you're going to be expecting, if we have vertical and horizontal asymptotes, the equation for the vertical asymptote would be x is equal to some number, and the equation for the horizontal asymptote will be y is equal to some number. And I have a little method to help you remember. For the equation of the vertical line, we know it's going to be x is equal to. So think about the letter x. On top of it, there's a v. V for vertical. Equation of a horizontal line is y equals some number. Well, let's take the letter y and let's turn it around. So we have something that looks like this. It looks like an H for horizontal. So that's another way that you can remember that. Anyway, why are we identifying horizontal, vertical asymptotes? Well, welcome to rational functions. In rational functions, we have weird looking graphs. We have something called discontinuities, meaning I have horizontal asymptotes, vertical asymptotes, and I have something called holes, or we call those removable discontinuities, because it's like a point, but you removed it. So it's a removable discontinuity, meaning it discontinues the graph at some point. So again, we have three different types of discontinuities: vertical asymptote, which is this right here, horizontal asymptote, which is this right here, and removable discontinuities, or your holes. Now, not all of our rational functions would have all of these, but it's important to identify them because we use these discontinuities as guides to draw our graphs. Because our rational functions are really weird looking. So they can look like this, or even like this. They're weird. But we use these discontinuities and we identify them so that we can use them as guides to help draw the rest of our graph. Alright guys, so I structured this review to mirror kind of like what the test is going to look like, so you would be more prepared. So as you can see, yes, a big bulk of this is identifying the different discontinuities and even the x and y intercepts. And again, all of these are just to help see what the graph looks like. Alright, so what we want to know about rational functions is first the forms. There are three different forms here, and you can see them right here. We have the standard form, and we have the factored form and the simplified form. Right? Sometimes the standard form would be simplified, and sometimes the factored form would be the simplified form. But we basically have three forms that we're dealing with, and each of those three forms have a purpose. And that's why we need to know how to convert them into each of those forms so that we can find all the different types of discontinuities. So let's kind of review that, shall we? Again, what I was saying, the three forms we have are standard, factored, and simplified. So let's look at the standard form, the first one. The standard form looks something like this, where I have maybe trinomials, and I have all of my degrees in decreasing form. The exponent of 2, this is the exponent of 1, and this one is technically the exponent of x to the 0 power. Anyway, it's decreasing exponents. And this form, this standard form helps you to find your horizontal asymptote. That's what it's useful for. However, if we wanted to factor these in factored form, so let's say that I have a factored form like this. And the factored form helps you to find your x-coordinate of the wholes. And then the final form is the simplified form. So when we simplified, it's usually in factored form. I can cross out something. Here I have x minus 1 and x minus 1. These can cancel out, and my simplified form would be x plus 2 over x plus 3 times x minus 5. It helps you to find the vertical asymptote and the y-coordinates of the wholes. And all these three forms, as you can see, gives us some bit of information about these discontinuities. Alright, so as you notice in this review, all of these equations in the front are given to us in standard form. So we need to find the two other forms so that we can find the discontinuities. So let's just do that first for all of these. Let's go ahead and factor. So basically, if you have trinomials anywhere, meaning expressions with 3 terms in them, you're going to want to factor it first, if possible. But for all of these, the factoring is possible. So notice in here, my numerator, I can't really simplify it, so I'm just going to leave it in the numerator as is. Now the denominator, I have a trinomial, meaning I have 3 terms. I'm going to see if I can factor it, and if it's factorable, I'm going to actually do it and see if I can simplify this further. So in review for factoring, we use the AC method. So we need to identify our A, B, and C values. Our A value is 1. Again, it's the coefficient of the quadratic constant. Our B value in this case is a negative 6. It's the number in front of our linear, x. So this is negative 6. And then our C value is going to be a negative 7. Don't forget to have that negative. If it's a minus sign, that's going to be a negative. If it's a plus sign, or nothing at all, especially right here, that's a positive. So AC method, I need 2 numbers to multiply to give me A times C. 1 times negative 7 is a negative 7. And I need 2 numbers, the same 2 numbers, to add up to give you whatever your B value is, negative 6. So let's start with 1s. 1 times a negative 7 does give you a negative 7. But added together, 1 plus a negative 7, well, yeah, it actually does give you a negative 6. So those are the numbers that work. A positive 1 and a negative 7. Positive 1 and a negative 7. So then you can just transfer it and rewrite it, because all we're doing is rewriting the denominator. This is a positive 1, so I'm going to put it x plus 1. And this is a negative 7, so you're going to put x minus 7. And again, I'm putting it in the denominator because all we're doing is rewriting this denominator as a product of 2 binomials. So we didn't change the value of it, we just rewrote it a different way by factoring. Now, because this is already factored, I can see if I can simplify it. Well, over here I have an x minus 7, and over here I have an x minus 7. Those are the same thing, I can cancel it out. So then your simplified form is simply 1 over x plus 1. So over here on number 3, I see my denominator is x minus 1. It's already a binomial. I don't need to factor that. I'm just going to rewrite it over here. I noticed that my numerator is a trinomial, so I'm going to try and factor that as a product of 2 binomials. A is 1, B is 2, and C is 1. So that means I want 2 numbers to multiply to give me my A times C. 1 times 1 is 1. And I need the same 2 numbers to add up to give you your middle term, which is 2. And the numbers that work are 1 and 1, 1 and 1. 1 times 1 does give you 1, and 1 plus 1 does give you 2. So those are the ones that work. So this is a positive 1, I'm going to put a plus 1. This is also a positive 1, I'm also going to put a plus 1. And because I can cancel something out, I'm going to go ahead and do it. X plus 1's cancel out. It doesn't matter which one I choose. That just leaves me with x plus 1 as a simplified form. Looking at number 4, I have a binomial and another binomial. Looking at the numerator, I can't really simplify this, so I can just rewrite this over here at 4x minus 1. And well, over here, this is a different type of factoring. I have a common factor here and a common factor here. The common factor between these two is the number 2. So I'm actually going to factor that out. So because these two have a 2 in common, I'm going to factor out that 2. 2x divided by 2 does give you x. And negative 6 divided by 2 does give you a negative 3. So yes, technically you can factor this, but it's not really necessary. As I can see, I can't really simplify anything else further. So my simplified form is just 4x minus 1 over 2 times x minus 3. And if you're confused about this, I mean, we can just go ahead and check. We just did the opposite of distributive. So if you wanted to check the correct factoring, just distribute it back. 2 times x does give you 2x, yep. 2 times a negative 3 does give you a negative 6, yep. It's the same thing, I just wrote it differently. So for our last one, number 5, these both have trinomials, so I'm going to try to see if I can factor both of them. So I'm going to have a product of 2 binomials on the top and a product of 2 binomials on the bottom. 2 numbers to multiply to give me my a times c values. 1 times 8 is 8. And I need those same 2 numbers to add up to give me my b value, which is 6. The numbers that work here would be 2 and 4. Because 2 times 4 does give you 8, and 2 plus 4 does give you 6. So this is a positive 2, I'm going to write it over here. And this is a positive 4, I'm going to transfer it over here as well. Now we still need to factor the denominator. So again with the AC method, because when you're doing math, it gets hot. A times C, 1 times 10. I need 2 numbers to multiply to give me 10, and I need those same 2 numbers to add up to give me my b value, which is 7. And the numbers that work would be 2 and 5. Yes, I know.
I'm helping.
Okay. So 2 times 5 does give you 10, and 2 plus 5 does give you 7. So I'm going to transfer it directly over. This is a positive 2, so I'm going to put a plus 2. This is a positive 5, I'm going to put a plus 5. And this is my factored form. Again, all I did was rewrite this fraction of trinomials as a fraction of products of 2 binomials. Anyway, as you can see here, I have x plus 2 on the top and x plus 2 on the bottom. Those are the same, I can cancel it out. So the simplified form would be what was left, x plus 4 over x plus 5. Now I have all my forms that I need. Now I can use those forms to find my 3 different types of discontinuities for each of them. Alright, so let's look at this one at a time. I'm going to find the vertical asymptotes first. So the vertical asymptotes is looking at the simplified form. In the simplified form, so this form, we set the denominator equal to 0 and we solve. This is my simplified form. The denominator is x plus 1. So to find the vertical asymptote, I need to set the denominator equal to 0 and solve. X plus 1 equals 0, set that to 0, and then solve. Subtract 1 from both sides, you get x is equal to negative 1. And that's the equation of your vertical asymptote, just like that. Or you can do the insiders lie thing. This is a positive 1. Insiders, they lied to you. This is inside the denominator, so it lied to you. It becomes a negative 1. Oh, let's hop over here to number 3, the vertical asymptote. Well, technically over here my denominator is 1. And if I set that equal to 0, that's 1 is not equal to 0. So there really is no vertical asymptote. And that's okay. Sometimes there's going to be no vertical asymptotes, sometimes there's not going to be any horizontal asymptotes, and sometimes there won't be any holes. So in this case, there's no vertical asymptotes because if I set my denominator equal to 0, there's really no solution here. Number 4, same thing for my vertical asymptote. I want to set my denominator equal to 0, so I'm going to do just that. 2 times the quantity x minus 3 equals 0, and then I solve for x. Well, before I can work inside the box, I need to work outside. Before you can work on a Rubik's Cube, you have to get it outside the box first. So got to divide both sides by 2, because that will cancel that out. 0 divided by 2 is still just 0. So really all you're left with is x minus 3 is equal to 0. And when you add 3 to both sides, you get x is equal to 3. And that's your vertical asymptote for this equation. Or again, you could have done the insiders, they lied to you. Negative 3 becomes a positive 3. And number 5, set the denominator equal to 0 in the simplified form. Remember, use the simplified form, it's simpler. To find the vertical asymptote, set the denominator equal to 0. I'm going to do just that. X plus 5 equals 0. So subtract 5 from both sides to get x by itself. So x is equal to negative 5. And that's the equation for your vertical asymptote for this equation. Again, vertical asymptotes, all you're doing is looking at the simplified form, set the denominator equal to 0, and then solve if possible. Alright, so we've already taken care of all the vertical asymptotes on here. Now let's take care of the horizontal asymptotes. Now remember, in horizontal asymptotes, we have 3 cases. We look in the standard form at the highest degree in the numerator and the highest degree in the denominator. And there are 3 cases. If the highest degree in the numerator is less than the highest degree in the denominator, your horizontal asymptote is automatically y equals 0. But in the case if the highest degree in the numerator is greater than the highest degree in the denominator, you would have no horizontal asymptote. If you have the highest degree in the numerator equal to the highest degree in the denominator, so case 3, you take the simplified form of the coefficients and set that equal to y. Let's look at number 2, for example. The highest degree in the numerator, meaning the highest exponent that there is a 1. Alright, so I have a 1 here, so I'll show it. And then the highest degree in the denominator is a 2. The highest exponent right here would be a 2. Well, 1 is smaller than 2. So in the case where the top is smaller than the other one, your horizontal asymptote will be y equals 0. On number 3, let's look over here. Here, my highest degree in my standard form is an exponent of 2. And my highest degree here, well, there's not one visible, but we assume it to be 1. 2 over 1. So that's greater than the one on the bottom. So in the case where the numerator one is bigger, that's option 2. In this case, there's no horizontal asymptote. So this one would be no horizontal asymptote. No Number 4, well, the highest degree here is a 1, and the highest degree here is a 1. So in that case, because they're equal to each other, I'm going to take the coefficients of each and simplify it, set it equal to y. Well, our coefficient here is a 4, and our coefficient here is a 2. 4 divided by 2 gives you 2. So y is equal to 2. And that will be your horizontal asymptote. Number 5, the highest degree here is a 2, and the highest degree here is a 2. They are equal, so again, I take the coefficients of each and simplify them. The coefficient, or the number that's supposed to be in front of this variable, is a 1. Same thing here, it's a 1. 1 divided by 1 is 1. Y equals 1. And those are all of your horizontal asymptotes. Now for our third and final discontinuity to help us graph, we have our removable discontinuity, or we know it to be our holes. Now for our holes, we look at the factored form and we see if we canceled anything out. So remember, you have a removable discontinuity if you actually removed something. If you have a removable discontinuity, that means you removed something from the factored form. So let's looky here. In the factored form, hey, we did remove something. That something was x minus 7. That is what I'm going to set equal to 0. And when I solve for x, that would be my x coordinate. X is equal to 7. So I'm only halfway there. I only have one part of my solution. I need to find my y coordinate. So again, what we do is we plug it back in, whatever we found, into the simplified form. Well, our simplified form is this right here. So I'm going to plug the 7 in place of x over here. So let me rewrite that simplified form. 1 over, and in place of x, I'm going to put this 7. 7 plus 1. And that gives me 1/8. And that is your y coordinate. And that is where your hole is in your graph. Now looking at this next one on number 3. In our factored form, hey, we did remove something. We removed x plus 1. That means we have a removable discontinuity. And to find it, we set whatever we removed equal to 0. X plus 1 equals 0. And when you solve for that, x does give you a negative 1. So that is your x-coordinate. You still need to find your y-coordinate. So again, you look at your simplified form and just plug it in. So our simplified form was actually x plus 1. And in place of x, again, we're going to plug in that negative 1, what we found. So negative 1 plus 1 gives you 0. And that is your y-coordinate. Negative 1, 0 is the point at which your hole exists for this particular graph. Number 4, looking at the factor form, I didn't cancel anything out. So because I didn't remove anything, there is no removable discontinuity. There is no hole, so I don't have to worry about that. And for number 5, looky here, we did remove something, and we're going to set that equal to 0 again to find our x-coordinate. So I'm going to subtract 2 from both sides. That should give you x is equal to negative 2. Again, that is only half of our answer. And then we go to the simplified form and replace x with whatever we found it to be, negative 2. So that is negative 2 plus 4 over negative 2 plus 5. Just leave it as a fraction. Negative 2 plus 4 gives you 2. And negative 2 plus 5 gives you 3. So your y value is 2/3. And that's the place of where your hole exists in this function. Now we need to find all of the x and y intercepts. And given the x and y intercepts, it helps you to draw your graph a little bit more precisely. But remember, the x intercepts look like the ordered pair some number comma 0. So in place of y, you're going to put a 0. But for the y-intercepts, I have an actual value in place of y, but in place of x, I have a 0. So those are the important properties of x-intercepts and y-intercepts. Alright, so knowing these properties of x and y intercepts, the easiest way, especially on your test, is to use your graphing calculator. You will have access to the graphing calculator. Whenever you're trying to find these intercepts, which will help you to graph, plug it in into your y equals. So just make sure that you're using the standard form, and whenever you're plugging it in, it's very crucial. It's important that you put the numerator in its own sets of parentheses and the denominator in its own sets of parentheses as well. And the fraction bar, that's the division symbol.
Go to your y equals and let's plug in this first one. So on the top we have open parentheses x minus 7 close parentheses divided by open parentheses x squared minus 6x minus 7.
So when you graph it, you do have a general picture of what the graph looks like. And yeah, we were right. The vertical asymptote is a vertical line when x is 1, as we can see here. And our horizontal asymptote is a horizontal line when y is equal to 0. So you can even check your work through here. Alright, so I want to find the x and y intercepts. Well, looking over here, I can see that I have a y-intercept, meaning I can see that my graph crosses the y-axis at some point. But because of the horizontal asymptote as y equals 0, at no point will my graph cross the x-axis. I can already see that there is no x-intercept, because there is no place in my graph where my graph will cross the x-axis. Now for your y-intercept, this is how you can find it. Go to second and then trace. The first option value will help you find it. And what that value option does is it lets you set your x value to any number and it'll find the corresponding y value. And to find the y-intercept, I know I just need to set x equal to 0. So just type in 0 and press enter. And it'll give it to you, and it'll even show it to you on the cursor. My y-intercept is 0, 1. And that's your answer. Now we need to do the same thing but for the other problems. So for number 3, I'm going to plug it in to my y equals, remembering to put the numerator in parentheses and the denominator in parentheses.
Open parentheses x squared plus 2x plus 1, close parentheses divided by open parentheses x plus 1, close parentheses.
So my graph looks a little something like a line. And you could even check my hole is at -1 because you can see there's an error, meaning the graph discontinues at this point, which we did say, hey, my hole exists at x is -1. So over here in my graph, it looks to me as if there's a y-intercept and an x-intercept. But remember, our hole was at -1, 0. Because of that 0 in place of y, I know that that was supposed to be my x-intercept, but it doesn't exist. So I really don't have an x-intercept. So this is a special case you want to look out for. So you don't have an x-intercept again. Now for the y-intercept, go back to your graph, go to second trace, and it's the first option, value. The y-intercept occurs when x is 0. Press enter. Your y-intercept is at 0, 1. Now for number 4, same thing. Put the numerator in parentheses and the denominator in parentheses.
X minus 1, close parentheses, divided by 2x minus 6, close parentheses.
So it looks to me that I do have a y-intercept and an x-intercept. So let's find our y-intercept first. Let's go to second trace, and remember it's the first option, value, and that occurs when x is 0. That occurs at the point 0, 0.16, repeating. This is actually just the ordered pair 0, 1/6. Now to find our x-intercept, we go back to second trace, and this time we go to 0. Zeros, remember, is another name for your x-intercepts, or your roots. So we're going to press that, and we can see visually that the x-intercept is somewhere around here. I'm going to scroll somewhere, obviously, to the left of it. Press enter, and it asks for the right bound. I'm going to scroll somewhere, obviously, to the right of it, and press enter twice. And my 0 is at 0.250, or it's the fraction 1/4, 0. 1/4, 0. And for the last one, numerator in parentheses, denominator in parentheses.
We have x squared plus 6x plus 8, close parentheses, divided by x squared plus 7x plus 10, close parentheses.
Right, so again, I have an x-intercept and a y-intercept. Let's find the y-intercept first, because it's the quickest one. Second trace, the first option is value, when x is 0. And my y-intercept is at 0, 0.8. And 0.8 is the same thing as 4/5, so you can also leave that in fraction form as well. But this is also acceptable because it's the same value. Now we need to find the x-intercept, so I can eyeball it and see it's over here somewhere. So I'm going to go to second trace and go to my second option, which is 0. Now I'm going to scroll somewhere obviously to the left of that, press enter, and then I'm going to scroll somewhere obviously to the right, press enter twice. And my x-intercept is at -4, 0. Again, there are ways to do this algebraically, but because you have your graphing calculator, the quickest way would just be to use these two options.